So in the last session, we've been talking about necessary and sufficient condition for a finite extension to be separable. And the condition is if E is a finite extension of F, then E is separable if and only if every element of E is separable. That is, if and only if alpha belongs to E, F alpha is separable. We are going to make use of this result in a couple of other theorems. Before that, we need a definition. Perfect field. A field is perfect if every finite extension is separable. So this is the definition, and we have a couple of theorems we need to prove. But before going into the details of those theorems, we need a result that is going to be used for those theorems. And that result is if f of x is equal to x to the power of n plus a n minus 1 x to the power of n minus 1 plus dash dash plus a0, if this polynomial is in f closure of x, I'm assuming that f is a field and f bar is the closure of f, and for m times 1 is not equal to 0, this means that we are adding 1 m times. We are not multiplying it, we are adding m 1 times. F of x to the power of m belongs to f of x. Then f of x belongs to f of x. See, this is a polynomial in f closure of f. F closure of x. But if there is an integer m with this property, then this is a polynomial in f of x, no bar. What I'm trying to say here is x square minus root 2 of x plus 1. This actually belongs to q bar of x. This does not belong to, this actually does not belong to, this does not belong to q of x. But if any power of this, probably x square minus root 2 x plus 1, this is actually not going to be true, but I'm just going to explain what this means. To the power of 2, if you expand this one, if this belongs to q of x, if this belongs to q of x, then this also belongs to q of x. But this does not belong to q of x, because if you expand this one, you have terms in terms of root 2. So this is not a real situation. The real situation comes in field of characteristics P or its extensions, not in this is a field of characteristics 0, so it may not come here. It definitely will not come here. So we'll give you a brief outline of this proof. The proof is very simple. Once you group together the coefficients of x to the power of mn, like f of x equal to the power of m is equal to x plus an minus 1 x to the power of n minus 1 plus dash 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 a0 to the power of m. So in this expansion, what will happen is you will have terms starting from x to the power of mn minus 1, mn minus 2 dash 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 to a constant. So this is actually going to be, you can verify this, it's going to be x to the power of n plus m times a n minus 1 x to the power of mn minus 1 plus m times a to the power of n minus 2 plus a function of, let's say g1 a to the power of n minus 1. In here you will have only n minus 1 times x to the power of mn minus 2. And the next term is m times a to the power of n minus 3 plus g2 of an minus 1 comma an minus 2 of x to the power of mn minus 3. Here you will have, in this term of x to the power of mn minus 3, you have terms of n minus 3, n minus 1 and n minus 2. But n minus 3 is always comes with m. Then a combination of these two. That is probably an minus 1 times an minus 2 times x to the power of mn minus 3. So this will be something, there will be something here, and there will be m times a to the power of n minus 3 x to the power of mn minus 3. This is how the term, this term will be. Not necessarily here, it will be much more than this when you keep expanding this. And then the final step, you will have plus dash 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 h0 to the power of mn. See, after some time, that is after nth term, n minus 1th term. This is the first term, then you take another n minus 1 terms. This will be the format. Then it changes, but we are not worried about the terms comes after n minus 1th term. To prove that this belongs to f of x, all we need to prove that all these coefficients belong to f. So we are not worried about the terms comes after this. We are only focusing on the terms n minus 1 n terms, sorry, not n terms, it will be n terms. an minus 1, n minus 2 dash dash a 0. These n terms we need to prove that they are in f. So in the next n terms the format will be like this. Then it goes differently. If you want to verify that, what we can do is x cube plus a2x square plus a1x plus a0 times a cube plus a2x square plus a1x plus a0. If you multiply this, you will start seeing this one. Here m is equal to 2 because you are just taking the square. See, if you take the, for example, here this n is equal to 3 and m is equal to 2. So this is actually going to be m times n, that is 6 minus 1, fifth term. The fifth term you get like this and this. And what is that going to be? a2 x to the power of 5, a2 x to the power of 5. And that is 2 times a2 x to the power of 5. And that is this item. X to the power of 4, how does it come? X to the power of 4 will this term multiplied by this term and this term multiplied by this term and these two together. So these two together is actually 2 times a2 x to the power of x square plus this is a1 x to the power of, so this is not square, it's 4 a1 x to the power of 4, and that is this one. This is actually 2 times a2 plus 2 times a1 to the power of x to the power of 4. And this is this term. And 2 of a1 is this. So keep on multiplying this, you will start seeing that for the n terms, we can evaluate you can find out whether these ai's are in f or not. So this is the expansion of this, and this belongs to f of x means all these coefficients of x to the power, this is actually x to the power of mn. All these coefficients of x to the power of mn, x to the power of m minus 1 dash dash dash, x to the power of 0, and that is mn, that is a to a0 mn. All these coefficients are in f because of this condition. What we need to prove is n minus 1 belongs to f. See, if this belongs to f, this implies m times a to the power of n minus 1 belongs to f. And m times 1 is not equal to 0. If it is 0, we cannot say that this is in f. But this is not equal to 0. And if this is, so that means it is actually is actually a b in f, and this is not equal to 0, that means b by a n minus 1 belongs to f. Sorry, b by m belongs to f, because this is not equal to 0. And that implies a n minus 1 belongs to f. Similarly, if you proceed with another n term, similarly, you'll see that a n minus 2 belongs to f, dash dash dash, a 0 belongs to f. And that implies f of x belongs to f of x. We need to do a couple of theorems on perfect fields. The first theorem is every field of characteristic 0 is perfect. 0 is perfect. Meaning, if f is a field and if it's finite extension, if f is a field of characteristic 0, then every finite extension of that field is separable. So we'll start with a field of characteristic 0. So proof. Let f be is a field of characteristic 0 and E be a finite extension. To prove that f is perfect, we need to prove that E is separable. So what we do is, we take an element from E, then show that that element is separable over E, f. So let alpha belongs to so definitely alpha is algebraic over f. So, and let f of x equal to the irreducible polynomial of alpha over f. And let alpha 1 dash dash alpha n be the conjugates of alpha, meaning these are the zeros of f of x. So then what we can do is f of x equal to pi of I from 1 to n x minus alpha I to the power of v. V is the multiplicity, where v is the multiplicity of alpha. This alpha is one of these alpha i's. And f of x belongs where? F of x is in f of x is in f of x. And actually that belongs to f prime of x. So f of x can be written as pi of I is equal to 1 to n x minus xi to the power of v. And that belongs to f of x. Actually, you need to write only f of x, that's fine. So this is actually what does this imply? This implies with the previous result, f of x belongs to f of x. Because if this power belongs to f of x, then the polynomial belongs to f of x. And that implies pi of I from 1 to n x minus alpha I belongs to f of x. And alpha i's are zeros of pi of I minus 1 to n x minus alpha I. But what is f of x? It is an irreducible polynomial. So you cannot find a polynomial whose degree is less than f of x still having all these zeros. But we found that there is a polynomial here whose degree is less than f of x and still has the alpha i's as zeros. That means this implies v is equal to 1. You cannot have v more than 1. If it is more than 1, then this is the irreducible. This is going to be the irreducible polynomials of alpha. And that implies alpha is separable. And that implies E is separable. And that's what we want to show. Our next theorem on perfect field is this. It's on finite field theorem. Every finite field is perfect. Every finite field is perfect. So what we need to do is, let's take one finite field and a finite extension of that finite field and show that it is separable. So let E, or let F be a finite field. Let F be a finite field. And E be a finite extension, a finite extension of F. When you say E is finite, that means E contains p to the power of n elements for some prime p and n greater than 0 an integer. And also we know that E is of characteristics P. So this implies f is of characteristic P for some and how do you show that E is separable? We need to show that E is separable. So we'll take an element from here and show that that element is separable over F. So let alpha belongs to E. And f of x is equal to the irreducible polynomial of f over alpha. And let alpha 1 dash dash alpha n be the conjugate of alpha. So the alpha is one of them. So this means f of x equals pi of I x minus alpha I to the power of v for some v, or we can say where v is the multiplicity of alpha. So now v is an integer, so we can take v as, let v is equal to p to the power of t. P is the characteristic of f. P doesn't need to be always and times e. P doesn't need to be always a factor of v. If it is not a factor of p, t is going to be 0 and e is going to be v. So always we can do like this. So this implies f of x is equal to pi of I x minus alpha I to the power of p to the power of t to the power of e. And f of x belongs to f of x. This belongs to f of x. And that implies pi of I x minus alpha I to the power of p to the power of t belongs to f of x. And because f is of characteristics p, we can write this as, this implies pi of I x minus alpha I to the power of p to the power of t is equal to pi of I x to the power of p to the power of t minus alpha I to the power of p to the power of t. So this is not actually f of x. So let it be a polynomial in alpha of, x to the power of p to the power of t. So this means that G is separable over F because G of x has G of x has all zeros with multiplicity 1, because there is no power here. It's not like this. And that means f of alpha to the power of p to the power of t is separable over f. Because alpha to the power of p to the power of t is a 0 of this. Alpha is one of them. And alpha is the only 0 of x minus alpha to the power of p to the power of t. Because there is no other zeros here. If it is just alpha, not alpha i's, I am taking one of them. And that means alpha is the only 0 of x to the power of p to the power of t minus alpha to the power of p to the power of t. Because you can write this polynomial like this because f is of characteristics p. Now let us consider an automorphism p from f of alpha to the power of p to the power of t. We want to prove that f of alpha is separable. But we already have f of alpha to the power of p to the power of t is separable. So what we are going to show is alpha belongs to this. Once you prove that alpha belongs to this, then we are done. So what we need to do is, let's take to f of alpha to the power of p to the power of t. And an automorphism. We are defining an automorphism. Define an automorphism by p of alpha or a in general is equal to a to the power of p to the power of t. Verify it is an automorphism. So that means it's on to isomorphism. So what does that mean? For what does that mean? That means for every beta belongs to f of, or we can say there exists a beta belongs to f of alpha to the power of p to the power of t such that sigma p of beta is equal to alpha to the power of p to the power of t. Because alpha to the power of p to the power of t is a member here, for every member here, every element here, there is an element here that maps to this. And but what is this? This implies b to the power of alpha to the power of, b to the power of p to the power of t is equal to alpha to the power of p to the power of t. Because by definition this is p to the power of. But what is alpha? Alpha is the only 0 of this. And f of alpha to the power of p to the power of t contains the zeros of this. So this implies alpha equal to beta. So what does this mean? This means that this belongs to, beta belongs to f of, beta belongs to f of p to the power of t. That is how we took it, right? That means alpha belongs to f of alpha to the power of p to the power of t. And that implies f alpha is equal to f of alpha to the power of t. But f of alpha to the power of p to the power of t is separable. That implies f of alpha is separable. And that implies E is perfect. And E is separable. And that implies F is perfect.